Let's start on lecture 24. We're going to continue on pick instruction set. We'll look at examples of control flow instructions. Here's a list of the control flow instructions. Go to, label, branch label, and relative branch using W as the offset, that's BRW. And also we have subroutine instructions, call, label, call, W. And we have corresponding return instructions from the subroutine, including return and return LWK, and also return from the instruction in interrupt service routine. Here are some examples. Go to there. There is assumed to be declared somewhere in your program. So there is a label. This is very similar to what we have for Intel instructions. The JMP instruction is the same as this go to instruction here, and they are unconditional branching instructions. So whenever the microcontroller sees this go to, it will go to that label immediately. Call task 1. Task 1 is the entry point of a subroutine. When you call task 1, the microcontroller will begin executing the instructions in the subroutine called task 1. And this call instruction will push the return address. The return address is the address of the instruction immediately following the call instruction. And this instruction, the address is going to be pushed onto the stack. And the purpose of doing this is to make sure that when the subroutine is completed, the microcontroller can come back to the correct point. Essentially, you have to come back to where you made the call. Return instruction is the last instruction you need to use in the subroutine. And this instruction will pop the return address off the stack. This is the opposite to the call instruction. It will get the return address out of the stack and use that return address as the next instruction to execute instructions. Return LW or RETLW is to pop the return address, but also put a literal value into the working register W. In our case, this is 5. So not only the subroutine will return to the caller when it sees this RETLW, there's one more thing this instruction will do, which is to put the number 5 into the working register W. Yeah, it's like a move instruction and then a return instruction. The purpose of doing this is to put the return value into the working register W. And for RETFIE, that's for return from the interrupt service routine and enable the interrupt. Now I'm going to introduce a few conditional branching instructions. Now these instructions are relatively new compared to the instructions we saw in 386. In 386, in Intel processors, we do have these conditional branching instructions, JNZ, JZ, JE, if you remember, or JCC, where CC is the condition code. So those are the conditional branching instructions in Intel processors. In PIC microcontrollers, we have these conditional instructions. You'll see they have slightly different operations than the conventional conditional branching instructions. The purpose of this instruction is to skip next instruction if condition is true. Now let me read this again. These instructions will skip next instruction if condition is true. In the past, when we look at Intel conditional branching instructions, the operand to those instructions are target address, like JNZ label, right? That's the target address. That's to say, if the condition is true, we're going to jump to that address. Here is different. We're going to check the condition. If the condition is true, we'll skip the next instruction. We don't give it a specific target for these instructions here in the pig. We just say, if the condition is true, you're going to skip the next instruction. There are two general forms, test bit and skip if bit is clear or set. And the other format is increment or decrement register and skip if the result is 0. Let's begin with the first, BTFSC. Okay, let me explain these letters one by one. B stands for bit, T stands for test, F, whenever we see F, that means we need the operand and we need the register operand. S is skip, C is clear. Okay, let me explain this again. Bit, test, a register, skip if that bit is clear. That's essentially what this instruction is trying to do. It's going to do bit test a bit of register F. If that bit is clear, this instruction will skip the next instruction, the very next instruction following this one. Let's read this again. Bit test a register, skip if that bit is clear. And that's the meaning of BTFSC. Now it takes two operands. First is the register, this lowercase f. You need to replace it with a real register. Second operand is B. This is a number. This number, the value is from 0 to 7 because we only have 8 bits. And the index of these bits in register F is from 0 to 7. So this is to test bit B of register F, where if this, the value of B is from 0 to 7, we're going to skip the next instruction if that bit is clear. Clear really means if the bit is 0. Okay, you following me? All right. Then the next one, BTFSS. The only difference is the last letter S. So this is to do bit test a register. I'm going to skip the next instruction if that bit is set, or if that bit is a 1. If that bit is a 1, we're going to skip the very next instruction. Okay. Then we have this DECFSZ. That is to say, we're going to decrement. This DEC is decrement. We're going to decrement the register F, and we're going to skip if F becomes a 0. DEC stands for decrement. F, that means we're going to need a variable, a register. We're going to skip the next instruction if F becomes a 0. This INC is increment, FSZ. We're going to increment register F. We're going to skip the next instruction if F becomes a 0. Okay. Now we have 4 examples here, starting from the first one, BTFSC temp1, comma 0. I'm going to do bit test, and the bit I'm going to test is in this register temp1, and the bit location I'm going to test is 0. So I'm going to test the least significant bit of register or variable temp1. I will skip the next instruction if that bit is 0. Okay, that's the meaning of this instruction here. Next instruction, BTFSS status, comma, C. We're going to do bit test on the carry bit of status register. We know status is a register that has several flag bits. One of them is carry bit. The C is in fact a number. Even though we can use C here, it's in fact a number. That's the index of the carry bit in the status register. So we're going to test the carry bit. We're going to skip the next instruction if carry bit is a 1. Okay, next instruction, decrement FSZ temp1, F. We're going to decrement temp1, and we're going to skip the next instruction if temp1 is a 0. Okay, this F here means the decrementation will update temp1. The last example, increment FSZ. We're gonna increment temp1 and put the value into the working register W, because I have a W here. And we're gonna check the result. If W is a 0, then we're gonna skip the next instruction. Note here, this temp1 is unchanged because this W here. Even you do the incremented value will be put into the working register rather than back into temp1. Okay, I hope you remember these 4 instructions. The way to remember these instructions is to really understand each of these letters in the upper code. BTFSC, that's the bit test. A register, skip it is clear. Decrement FSZ is to decrement a register, skip if the result is a 0. Okay, now we're going to work on this example. Show the values of all changed registers after each of the following sequences. Let's just do the first one on the left, case A. Okay, let's walk through these instructions. First instruction, move F, A, comma, W. A is a variable, and we assume it's declared before. Note this A is different from this 0xa. The 0xa is the A in hexadecimal, that's a literal, that's a constant number. This A is a variable. And because this W, this indicator, we will actually copy the value of A to working register. So we're going to assign the value of A to the working register. The second instruction is subtraction LW. We're going to subtract W from the literal number. Yeah, again, this A is the variable named A. This 0xa, this is the number. This is the A in hexadecimal. So what we're doing here is we subtract A from 10 and put the result into the working register. You follow? Now when we do subtraction, if the result is 0, then the 0 flag in status register will be updated. So if it's a 0, the 0 flag will be a 1. So check this instruction, BTFSC, status, comma, Z. We're going to do bit test. We're going to test a register, a bit from it. And if that bit is clear, then we're going to skip the next instruction. Okay, it takes a little bit of time to get used to these complex opcodes. So this instruction will test Z, the 0 flag, out of the status register. It will skip the next instruction, which is this one, if Z is a 0. Let me repeat that again. It's very important you understand this. This instruction, BTFSC status Z, will test the 0 flag out of the status register. It will skip the next instruction, which is this one, if the 0 flag is cleared. Okay? So let me say it another way. We will skip the next instruction if this subtraction does not result in a 0. If the subtraction does not result in 0, this Z will be a 0. This 0 flag will be a 0. And in that case, we're going to skip this go to instruction. Right? Do you follow? Do you follow? Let me explain this again. For this subtraction, if the result is not a 0, it will clear this 0 flag. And in that case, this BTFSC will find that 0 flag is a 0. That's the C. That's cleared. So it will skip the next instruction, which is this one. It will skip this go to instruction. And in that case, it will execute this increment. And then go to L2. Okay? Now let's come back here. If this variable A indeed has a value 10, or A in hexadecimal, so when you do the subtraction, you do hexadecimal A subtract hexadecimal A, that's a 0. So this subtraction instruction will set 0 flag to be a 1. When it gets to here, BTFSC, it's going to check the 0 bit. Now it's a 1, right? So will it skip or not skip? 0 flag is a 1, and my condition is clear, so I will not skip the next instruction. Do you follow? So I will not skip the instruction, so that means I'm going to execute this go to L1. So I'm going to do this, decrement B, comma W, and then going forward. So the high-level operation of this piece of code is to really do check whether 10 minus variable A is 0 or not. If it is 0, then we're going to do B minus 1 to A. Otherwise, we're going to do B plus 1 to A. So the takeaway message of this example is that often the time, after this BTFSC, or this conditional branching instructions, often the time you will see a go-to instruction. Because depending on the checking, we may skip this instruction or not. If we skip, so we're going to do some case. Otherwise, we're going to execute this go-to and do the other case. This is how you do the if then else in the PIC microcontroller. So the BTFSC is gonna check whatever bit in whatever register. So because we have status, comma Z, so we're gonna check the 0 flag or the 0 bit in this status register. This Z is in fact declared before. That's probably either 4 or 5. I don't remember the exact number. But with using Z, you will get to the exact 0 flag bit in the status register. Yeah, those are reserved values. You should not use them to, let's say, you declare variable Z or declare variable status. This part B is very similar to part A. It's a if then else statement. Although the condition we're checking here is different from the previous one. I will not go very much into these details, but you can go through these instructions, especially this BTFSS instruction, to see what other cases you're going to take one, well, what other cases you're going to skip the next instruction, and what other cases will not be skipped.